This video is going to run through NMR. Specifically, it's going to be looking at carbon-13 NMR. At this point, you may or may not be aware there's two different types of NMR. You've got the carbon-13 NMR and you've got proton NMR, or hydrogen NMR. And basically, what we'll do is I'm going to split those into two videos. This one purely being carbon-13, and then hydrogen or proton NMR being a separate video. But the initial point will be the same, the initial explanation as to sort of a bit about how NMR works, a bit about the standard used, and a bit about the solvent. Then it differs after that, really. So first of all, what is NMR? Well, NMR is an analytical technique. So we use it to analyse substances. So analytical technique, and it comes into Unit 4 of the AS spec. So at the end there, we're analysing, part of the organic chemistry, we're analysing various compounds, organic compounds. What does it stand for? Well, it stands for nuclear magnetic resonance. Now, you don't have to really know much about how the process of it works. In fact, you don't need to know anything about how the process of it works. You just need to know how to interpret the spectra that are produced at the end once the process has occurred, and how you can interpret those and interpret molecules as well. Look at molecules and decide what the spectra would look like. So it's all about the actual molecules themselves, not the technique really. But that said, I'm going to go very briefly into sort of how the technique works, and just a little bit about it for more sort of background rather than anything. But bear in mind, you do not need to know this. If you don't understand the next sort of couple of minutes, fine. And I'll break the video down into little markers in the description, so you can by all means skip this first part and go straight to the standard, which you do just know. So how does it work? Well, the way it really works is you need, when we look at nuclei, if there is an equal number of protons, or I'm sorry, not equal, if there is an even number of protons or even number of neutrons, you will find that spin is 0. And what I mean by spin is really it's a property that nuclei can have, which is very important, because this is really what the NMR, the nuclear magnetic resonance, that's what it's based on. So that's an oversimplification, but it works. So if you look at carbon, then, for example, of carbon, carbon has 6 protons, and in the case of carbon-13, 7 neutrons. And it's because of this 7 neutrons that actually the carbon-13, the nuclei of a carbon-13 atom, possesses spin. And it doesn't matter about the spin, it possesses half spin, you know, that spin, but that doesn't really matter. It's just a property that it possesses because it has this odd number of neutrons. And that's more than you need to know, but that's just what happens. Okay, they're not paired up, we end up with a bit of spin. But what that means is that actually this carbon-13 nuclei, or nucleus, sorry, acts like a bar magnet. So you remember those bar magnets, you use them at school. That's not what I wanted to do, I wanted that to be blue. And obviously the nice little red bit as well. So you use the bar magnets, and this is kind of how the nucleus, sort of, you could liken it to a bar magnet. It exerts a small magnetic field. And what that means actually, though, is that if I use a bigger magnetic field, I can actually change this. And what I can do is I can flip it. So I can turn this into this. So I flip it completely over. And in doing so, I will find that change, that flip, is something that I can measure. And it's the measurement that is plotted onto a spectrum, which I'll show you in a second. So again, you don't need to know really any of this. It's just to give you a bit of a background. So just to recap what I've said, if a nucleus has an odd number of protons or an odd number of neutrons, it can possess a property called spin. of which means it can be used in this NMR, and hence the reason obviously carbon-13 can. Carbon-12 cannot, because it has an equal number of protons and neutrons, therefore no spin. And that's an oversimplification of what I'm saying here, but it works. What we do then is we put our sample, whatever it is we're trying to analyse, and that will make a little bit more sense later on when I look at actually how it all works. We put our sample into our NMR machine. We apply a magnetic field, and it will cause some of the nuclei to flip. And in doing so, that's a change we can measure, and we can put that onto a graph, onto a spectrum. And I'll show you really the spectrum, or the spectra look a lot like this. So this is the carbon-13 Nmr spectrum for ethanol, and you can see it has a nice just flat blue line and then two peaks here, and that's very important because that indicates. And you might think, oh, there's two carbons, two peaks, and you are right, yet also wrong. And I'll go through what this. I'll use this again later on as an example. But this is basically what we're measuring here. This is the measurement. Each one of these is a measurement of that nucleus flipping. And quite a good analogy I read, and I can't remember where I read it now. It was on, I think, an American university's description of NMR. Was it's like tuning a radio. And basically what they do is you can liken, they change the frequency of the electromagnet, and depending upon the frequency depends on the carbons that will, the nuclei that will flip. And so what you can do is you're tuning your radio, static noise, static noise, static noise, and here you go, and then you tune into a station, and then you go again, and then you tune into a station. So it's that they likened it to, you don't tune into every station at once. You just tune into one at a time. And again, the way this is done in various research labs and all the rest is that a different frequency is applied, and basically the nuclei are detected, and the flipping gives us a peak. Now again, you might at this point have no idea what's happening, but hopefully by the end it'll make a little bit more sense when it's all sort of pulled together. Now what I am going to just look at very quickly now is sort of when we do this, when we actually put our sample into our NMR machine. So in the case of ethanol, we've put our ethanol into our NMR machine, and what we want to take a reading. Well, these readings are compared to a standard, and that standard is one that would have a line that appears at 0, and so that's a delta equals 0. This x being delta here, and you're given various values on your in your data table, but for the carbon-13 NMR, not really required to use that. It's the hydrogen NMR where you tend to be needing to use those. But anyway, so this delta value here is 0, and that's because of, and I've drawn that on, it's removed when you tend to look at the spectra, and that's because of this thing called TMS. Now TMS stands for tetramethyl silane, and it's very important. It looks something like this. So CH3, 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 CH3. So this will make sense in a second when I say this, but it's the reason this is used is because all hydrogens and all hydrogens and all carbons are in the same environment. And again, just bear with me for now. Just go through this, and you can by all means rewind and all the rest to work out what's happening. They're in the same environment. And that means this produces a single peak like this, a single peak which can be removed afterwards. And what happens is all of these peaks that you see on both carbon and on proton NMR are all produced as a comparison. This is used as a standard, and they are all compared to this. And this is arbitrarily given the value of 0, and all the rest have values that that are produced based upon this being 0. So it's a comparison to this TMS, this tetramethyl silane. So you could also abbreviate it down to CH3 for SI. And if you ever are interested in learning more, you can also see it written as Me4, which is the methyl, and then SI as well. So just another couple of ways you could write it out. I probably wouldn't write anything like that in an exam, in all honesty. I would probably ignore that and stick with this. And occasionally you do get questions that ask you to draw this out. Draw the molecule that is used as a standard in this carbon-13 NMR, and we'll just stick this down. Okay, if it's asking for displayed formula, obviously you're going to draw the CH3s completely out as their full bonds. So this is the standard used, and this, I do apologise, this may seem at the minute a bit sort of a bit bitty going from here to there, but hopefully at the end it sort of all gets tied in together slightly. It's just trying to get the sort of a reasonable order for it all to happen. So that's the standard used. The other thing to look at before we actually start looking at the actual peaks themselves is that when we come to take these samples, or we put our samples into our NMR machine, they're put in as liquids. So they need to go in as solutions, as liquids. To do that, we have to use a solvent. Now, questions on exams they tend to quite like asking is, why would you use a solvent such as CdCl3 as opposed to CHCl3? Now that tends to come up in the hydrogen question. And so I'm going to ignore that a little bit for now, but the reason being that proton NMR is based around hydrogens. Well, this D stands for deuterium, which is an isotope of hydrogen, which is like that. It's basically slightly different, and that, I'm going to say, it doesn't get picked up in the spectrum. It's a slight lie, but it doesn't get picked up in the spectrum, certainly not like the hydrogen would do in the CHCl3. And this here is classed as, you'll see this written down sometimes, deuterated chloroform. But in terms of the carbon NMR, this is still the solvent that is used. It does contain a carbon, but that again, it's a very distinct peak that can be removed later on, and that's the beauty of it. So that's the solvent used, CdCl3. Again, that will make more sense once you've looked at the proton NMR as to why you'd use the deuterium and not the hydrogen. But it's a point worth noting now anyway. So let's go down here. I'm going to put ethanol back up, that spectra. And now I'm going to say, well, we're going to look at, well, why are there two peaks? What are these two peaks actually representing? And that's really now, this is where the marks are going to come. The bit before, you'd perhaps pick up a couple of marks here and there, naming the solvent, naming the standard. But this is really now where the marks are going to come in. And it's actually very straightforward. There's nothing difficult about, particularly the Carbon-13 NMR. There's nothing difficult about it at all. So why two peaks? Well, the thing is here, each peak is equal or represents a different carbon environment. At this point, you'll be thinking, well, what is a carbon environment? Well, that's a very good question. So this term carbon environment, the best way really to look at this is to compare it, is to actually look at molecules. Now we'll come back to the ethanol in a second. Let's take a molecule of ethane. So ethane, CH3, CH3, or C2H6. Looks like that. Now, if you think back to what I said at the start, if you missed the start, then it doesn't really matter too much. But when we apply our magnetic field to our molecule, to our sample, it affects the nuclei. And obviously, in carbon-13, we're looking at it affecting the nucleus of a carbon-13 atom. Now, that nucleus here is affected by what is around it. So what is bonded onto this carbon will affect it, and therefore, essentially, different carbons, or carbons that have different things bonded onto them, will feel the magnetic force differently. So I'm going to write that down. So carbons with different bonds will feel the magnetic field differently. Now, apply it to this scenario here. So this carbon has attached to it 3 hydrogens and 1 CH3, 1 methyl group. This carbon has attached to it 3 hydrogens and 1 methyl group. Therefore, actually, these 2 hydrogens, in terms of NMR, they are classed as having the same carbon environment. So these 2 hydrogens have the same carbon environment. And again, once more, just to make that really clear, the reason is that each one of these carbons, look at them individually. This carbon first has 3 hydrogens and a CH3 group bound to it. This carbon has 3 hydrogens and a CH3 group bound to it. Therefore, they are in the same environment. They are not the same carbon. They are 2 carbons, but they are in the same environment. And actually, if we would look at the spectrum, it would look like this. And there you go. You can see now there is only one peak. Therefore, 1 carbon environment. So 1 carbon environment, 1 peak. And that's because in this case we have this, what you can often actually look at it in terms of, I was going to come on to this in a minute, but I'll look at it now. It's if there is symmetry within a molecule, then that's an easy way to look at it in terms of the carbon environment. So this here is perfectly symmetrical. Therefore, we know that this side is going to be equal to this side in terms of what's bound onto it. Now, if this was here a chlorine, this would not have 1 peak now. It would have 2 peaks. But, of course, it isn't a chlorine. It's a hydrogen. So let's look at another example. See how this goes. So go across and let's have a look at this. So this is the Nmr spectrum for propanone. Now propanone's a favourite, and molecules like this are favourites in exams. And if you draw out propanone, and this is what I'd always recommend, if you're ever asked about a molecule, draw it out. Okay, that's the easiest thing. We'll draw this actually in its full. So this is propanone. Like this, nice little ketone, the smallest ketone we can get. There we go. So let's have a look at the carbon environments here. This is saying 2 peaks, therefore 2 carbon environments. Well, let's have a look. Where do they exist? I'll circle them in different colours. So this carbon has 3 hydrogens and it has a COCH3 bonded to it. So this carbon here has 3 hydrogens and then a COCH3. This carbon has 3 hydrogens and then a COCH3. So straight away I'm looking at this and I'm going, well, I know for a kick-off, these two, here, right colour, these two are going to be in the same environment because they have exactly the same bound to them. 3 hydrogens, COCH3, COCH3. They both have exactly the same bound to it, which leaves us this little guy in the middle here, which obviously must be a separate one, because this one here, it has oxygen, and then it has 2 methyls. So a completely different environment. This carbon, the nucleus here, is being affected differently based on what is bound to it, whereas these two have the same effect because there are the same things bound to them. And again, if we look at this whole idea of symmetry, line down the middle, line down here, we have this symmetrical element here, and that's a good way to actually look at the molecules. It is a symmetrical element, particularly when methyl groups are joined, and they love to trick you out in that. So, 2 peaks. Now, if we go back up, or back aside, I think it was, there we go, to ethanol, then actually now we can look and we can say, right, well, ethanol, what was happening here? Well, draw ethanol out and see what it looks like. So CH3, CH2, OH. So here we've got a CH3, we've got a CH2, and we've got an OH. Well, this time we can see this C has 3 H's, and then it has a CH2OH joined to it. This C, on the other hand, has a CH3, 2 H's, and an OH. So different things again. And that's the key thing now. These are in different environments. So in terms of the exam, there would be 2 peaks seen, and here we go. Ethanol, 1 peak, 2 peaks. Now if you were to look at your table on in the exam that you're given, you would be able to deduce which peaks are this, or which peak is which, and I'll just show you. And if we look at this, we can actually see that within our molecule here, we look on our table, they are quite a bit of a pain to read sometimes, but this one here, the alcohols, ethers or esters, 50 to 90, we have a carbon which is bound to the oxygen there, and we can see that's going to be this carbon here. So this one, this peak is going to correspond to this one here. The other peak is going to correspond to this top one here, where we just have a more simplistic carbon-hydrogen setup on the go. This comes into play more, as I said earlier on, in the proton NMR, less in the carbon-13. But I don't think I've seen a question on this on the recent series going back to January 2010 or whatever it is, June 2010, that actually has had a question like this to do with carbon-13. But again, it's something to be aware of, and once you've done hydrogen NMR, you will have a better understanding of that anyway. So, what I'm going to do now, going to give you a few molecules, give you a chance to actually do some practice and decide how many peaks do you think these molecules have got. So I'm going to give you two. I'm initially going to not draw them out, just to get you to draw them out, as you should be able to do, because it's just a normal nomenclature. Work out how many peaks they've got, and then I'll go through them. And obviously pause the video and all the rest. So first molecule I'm going to look at is 1-methyl ethyl propanoate, and second is but 3N2-one. So second one a bit more of a difficult one to draw, but pause, have a go at that. Okay, so first one, 1-methyl ethyl propanoate, also known as isopropyl propanoate, looks something like this. So start with the propanoate part. So propanoate is here, CH3, CH2, going down to the O, 1-methyl ethyl, so let's put that up there, 1-methyl ethyl, just like that, lovely. So how many peaks do we have? Well, hopefully you've got an answer, and let's look through this. So let's see, this carbon, are there any other carbons that are bound to exactly this, that have exactly the same bonds as this one? No, there are not. So this is an individual carbon. I'll tell you what, actually, no, I won't do it as a tick, I'll do it as a circle. I'll circle each individual environment. I think it's the easiest way to do it. This carbon, same question. No, there are none. This carbon, same question. No. This is now where it gets a bit, not necessarily tricky, but you've got to be careful. Exam boards love this they love this scenario right here, because this is the trick. Now this carbon is separate to the other two, because neither of the other two have anything bound to it, but these two actually are in the same environment. They are in the same environment. Another way to draw this out, which would make it look a little bit clearer, but I purposely didn't do it, is if you were to imagine this carbon here, just with the hydrogen over there, we can ignore that hydrogen, and then we have this CH3 and this CH3 like this. I've just redrawn this end part here, and that would go to the O, obviously, up to the CO over there. You can see now, as I said before, we've got this symmetry. Now maybe not symmetry through the whole molecule, but we can see that this and this, they have exactly the same bound. This carbon has 3 hydrogens and then the rest of the molecule. This carbon has 3 hydrogens and then the rest of the molecule. So the answer to this first one would be 5 peaks. So 5 peaks, 1, 2, 3, 4, 5. Let's have a look at the second one then. So if you haven't done the second one, do it now and give it a pause. If not, I'm just going to rub this out. So 5 peaks, the first one. Let's draw out the second one and see what we've got. So a horrible one to draw really. So we've got 1, 2, 3, 4. But 3N2-one. So we'll do 2 there, 1, 2, 3. But 3N2-one. We can change that. 2-one over there, and done. How many peaks then? So different colour this time. Do exactly the same as we did before. So we've got this one here. Anything joined, any other carbon in this environment that has exactly the same thing joined to it? Nope, don't think so. Separate peak. This one, same question. Separate peak. This one, separate peak, and this one, separate peaks. This one, 4 peaks, because there are 4 environments. Just to prove I'm not lying, there is the actual carbon-13 peak, or spectrum, sorry, for the but 3N 2 ohm, and this is it here, and you can see 4 peaks corresponding to these 4 carbons right here. And again, you could use the data sheet from before to actually determine which peak is which. So if we look at this table again, just to draw on what I said, if we look at the various portions here, we can say we'll number these carbons, and then we'll number the peak that corresponds to it. Start at the left going in, we've got, oh sorry, that's the right, not the left, we'll start at the right. We've got 2 carbons here attached to a double bond. Well, both of those are going to come under this guy's here, which is these 2 close ones here. So not worrying about which is which. 3 and 4 are going to be those. We go to the other side, we've got a carbon double bonded to an oxygen. We've got a carbonyl group there that's within a ketone, so it's going to be this guy here. So we know that 2 is going to correspond to that one, which means 1 must be over here, which is exactly as we would expect. If you're going to get this in an exam, it is going to come up easily. And again, I've not seen this in terms of carbon before, and this is a slightly more difficult molecule, certainly with this one here. But the hydrogen, you do need to know how to do this, but that'll be covered in that video. Right, a couple other examples that I've taken from exam papers. I thought it would be wise to look at some aromatic examples, because I think people can often get a bit confused and they actually forget that the ring is made of carbon. So actually imagine here you've got a carbon, 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 and then you've got a carbon. That means, and again, symmetry is very important with this one, and this is actually a lovely molecule for it. You can see if you draw a line down here, you have that glorious symmetry. We can ignore this group and this group and this group because actually they don't contain any carbon, but obviously we can't ignore them in terms of what's attached to what. Now if we do symmetry based on this top point here, we can see that this carbon is individual to the rest. There is no other carbon that has exactly that bound to it, because this has that methyl group here. And the same applies to this carbon here. There is no other carbon that is in that same environment. Now comes the trick. These are in the same environment. Each has an NO2 group, and then the rest of the molecule. These 2 are in the same environment. Each of them has the same bits, but obviously just reversed. And this carbon here is in its own little delightful environment. So 1, 2, 3, 4, 5 peaks would be seen on the spectrum for this. And this was a past exam question. You were given this. This is TNT, in fact, trinitrotoluene. You were given this and asked, basically, you know, how many peaks would you see? And this is a reasonably easy example. The next one, a little bit less so. Here we go. This is something in the exam where this is called Ethanol. And again, how many peaks are in this? And what initially looks like a very, very confusing molecule, actually, if you break it down, isn't too difficult at all. And I would always encourage, as I do, as I have done in the past, to actually circle the carbons as you go along. And that makes it very easy, particularly in the carbon NMR. That's a very easy way to work out what's in what environment. So start at the left this time. Carbon, 1 environment there. And you may wish to have a go now to try and work this out. Pause it and see if you can get it right. Go to the right, same again. Hit our nice little benzene ring here, the nice little aromatic portion. So remember, each one of these corners is a carbon. Well, that one's not in the same environment as any others, so that's 1. These 2, because there's that symmetry down the middle of this ring, we have that there, another one there, this carbon, yep, still go, more, another one. Right, this is the same as that example I used earlier, and imagine this is drawn out as, again, ignore that hydrogen, drawn out like this. That becomes a lot clearer, and you can see that symmetry. Each one of these carbons has 3 hydrogens and the rest of the molecule bound to it. 3 hydrogens, rest of the molecule. So these 2 are in the same environment. This one is on its own. And when we add that up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We get 11 peaks, which is the correct answer. So 11 peaks for this molecule here. If you're struggling with that, really take a look and watch back and try and work out what's happening, and leave a comment or whatever if in terms of if you're struggling to work out how this is happening. Final portion then, final question to look at. Another way they can ask things is like this. I'm running out of room. So you're given a question here where it's just giving you the peaks, and it's basically now asking you to draw the molecules based on the peaks. Now you can see space for working, have a bit more space under here, it's worth 2 marks. If you're finding this really quite difficult, I wouldn't bother spending too much time. I'd go to the end of the exam and I'd use any spare time on this. I wouldn't spend 10 minutes on this because you're only getting 2 marks from it, so it's a waste of your time. So compounds F and G have the molecular formula C6H4N2O4 and are both dinitrobenzene. So straight away, I'll continue reading first. F has 2 peaks, G has 3 peaks. So straight away, I know that I'm based around a benzene, which makes this a little bit easy. So that gets rid of my C6 H4. We know that we've got dinitrobenzene, so again that's there. The following part, the N2O4, so there's nothing else attached, just the 2 nitro groups. But we've got to look at where to attach them in order to get 2 peaks and 3 peaks. And we know that F has 2 and G has 3. Well, if we attach them next to each other, I'm not saying this is the right one here, I'm just going to say, well, what would this look like? What would we get peak-wise? Now, another way to think of this is actually to redraw it slightly, so it looks like that. No, it shouldn't be wonky, it should be completely straight, but that would be one example. Now, how many peaks would we get from that? Well, this carbon here, remember there's a carbon at each corner, has the NO2 and the rest of the molecule. This one also has NO2 and the rest of the molecule, so these are in the same environment. These two, well, they're in the same environment as well, and we can see that symmetry aspect now again down there. These two, so actually I've picked the right one. This is actually the correct one for G, just completely flukily there. That is the correct one for G. F, so I need to find one now that has 2 peaks. F, well I know it's, so this is correct. I know it's got 2 peaks, it's got to have 2 nitros joined on. Well, straight away I'm gonna put them here and I'm gonna see what it's like. And this is a lot of this is a bit of the way I play this is a bit of guesswork, trying to work out what's happening really. So is this going to work? How many peaks have I got here? Well, this is a strange one now, because if you think of it, these two are going to be in the same environment, because each of these has NO2 and the rest of it joined to it. Well, because of the symmetry going 2 ways on this one, all 4 of these, that's terribly drawn, but that one, that one, that one, and that one are all in the same environment. Therefore, this is correct and would actually only have 2 peaks, and that is a tricky one to think of. The 3 peaks, you look at it and you think, oh, 3 peaks is more difficult. It's actually the easier one. And there you have it. So there's been a few exam questions there. By all means, go back over those, re-listen, watch, and see how you find it. And as I say, as always, I hope that's been of some help.